Okay. All right, let me just check on you guys real quick. Okay, you guys look good. Okay, yeah, sorry for the delay. Man, if it's not one thing, it's another. Like usually I have such a hard time getting the image to push. That one went off like no trouble, right? So today the trouble was something like it was so wild. It was basically trying to log into my box account, log into my account so I can pull the information. I'm like, it's supposed to be single sign on and this, that, and the other. And I was like, on one page I'm logged in, but then when I use the same information on another page, it wouldn't work. So anyway, I finally got to the bottom of it. And I think we're good to go. Didn't really intend to be this late, but it took me like 10 minutes to get that thing to work. And that was something that usually does not happen, but that's neither here nor there. Okay, guys. So we are here. Welcome. You are present and accounted for. We are in a home stretch, right? So I want to say everything wraps up like that typically it's that first week of May. I'd have to go back and either look at the syllabus or look at an official calendar to get the official dates. But, let me see. So as soon as we finish chapter 4, we're going to be ready for exam 2. We've officially completed chapter 3. And so we're now moving into chapter 4, which is anti-differentiation. And basically what that is doing the reverse of differentiation. So when you take the derivative, you get an answer. Now we're going to start to explore some techniques and concepts where we start with the answer and work backwards, right? This is the main class where you get an introduction to integrals and anti-differentiation. Okay, as usual, if you have questions, feel free. Hopefully my image is being pushed because it looks frozen. Is this playing? Oh, can we go live here? Let me make sure it's working. Let's see. Okay, I think it's fine. I think it's okay. I think it's just a little bit of delay. I guess I can leave it like that. Okay. So I'll trust that and assume that it's working. Yeah, again, if you have questions, comments, or concerns, feel free to unmute yourself. Look, guys, also, I already made the disclaimer about emails. I do the best I can. Again, I still encourage you to email me, but when I'm not with you guys, I'm just trying to survive out here, right? So if I don't respond to your email, you want to ask me during class, right? Okay. And again, the rhythm from here on to the end is that we intend to basically do one section a day. Man, this is like so far behind. Okay, let's go like this. Oh, that's not a good omen. I don't think the image is being pushed. Oh no. I don't think you guys can see my image. Yeah, because I'm not getting my confirmation. No, it was working and now it's not. All right. Okay, so now we have let me get these students first before I start doing this, fooling around with this thing. Because it doesn't look like the image is pushed. Okay, let me that's fine. I know he was here. Okay. Let me repush this image because I think it's not being pushed. Because when I look at my confirmation, I don't see what I need to see. Share my screen, start the broadcast, and optimize. Let's see if that works. My confirmation there. Oh, I know another thing that I could do that. Okay, that's no. It looks frozen. All right. I guess I gotta figure out a different setup. I don't understand why it doesn't work. Let me unplug it because sometimes that affects it. And I restarted it before class. Like my whole intent was for the stream not to be an issue, and it still is an issue. Okay, let me just do like this. I guess I gotta figure out a different setup. I don't understand why it doesn't work. Let me sometimes that affects the broadcast. Now let me see if I go full screen, optimize, and I think if I go like this, that helps. Okay. I should see 4.1 anti-differentiation. I think if I go like this, that helps. Should see 4.1. Nope. Let me try again. I don't know. Okay, stop the share. I'm gonna go like this. Okay, I should see chapter 4 integration. Okay, I should see chapter 4 integration. Yeah, guys. I don't really know. Let me try this. 4.1 anti-differentiation. Still nothing. So I'm getting my nerves. Yeah, I don't know. And this is something like it's never really been like this before. This is something like this recent. We just rebooted again. Okay, we should see 4.1 anti-differentiation. Finally. Okay. I had to reboot it a second time. Like, it's so weird. I definitely rebooted it like right before class started, and it was kind of working. It seems like it's working now, so I'm just gonna go with it. Let me check on you guys one more time. I know, we have a hard time getting started, but we're here. That's about the best we can do. Okay, so let's take a look at this. So, okay, again, we gave a brief synopsis of what anti-differentiation is. Again, in the previous chapters, we've been, exploring the derivative. We take the derivative, whether the derivative is going to give us the slope of a tangent line at a point to a curve. And so we take the derivative, we get an answer. So now we want to explore techniques where, given that answer, we want to work backwards and see, can we get to some form of the original? And that's what anti-differentiation is. Some objectives here: we like to find an antiderivative of a function, evaluate indefinite integrals using basic rules of antidifferentiation, use initial conditions to determine an antiderivative. Okay, so the antiderivative of f is a set of functions f of x plus c such that d by dx of f of x plus c equals the lowercase f of x, right? So when the antiderivative of the set of functions such that when you take the derivative, they give you f of x. The constant c is called the constant of integration. Okay. So anti-differentiating is often called integration. To indicate the antiderivative of x squared, it's going to be x cubed over 3 plus c. All right. We write the integral of x squared dx. Let me do this. Yeah, it's not being pushed. I just saw it. Yeah, I don't know. It's like the first image comes and then it just stops for some reason. Again, this is why I made my pre-recorded videos. So anything that I would say here, it is recorded already, essentially. That is exactly why I made those pre-recorded videos. Let's see if I can get this to work. Stop share. Okay, let me give that a moment to just process. Okay. Let's share the screen. Start the broadcast. Optimize the video. Let me see if I can see the desktop. Start the broadcast. Optimize the video. Yeah, I'm not sure, guys. I just might not be able to do these live the way I'd like to until I can figure this out. We might have to just rely on my pre-recorded videos. Like, that's exactly why I made those. It's never been like this bad in the past. And I don't really know why it's behaving this way. Hit play. Yeah, I'll get them in a moment. Stop the share. Just give me a moment. Here. What else could I do different? Share share the screen. Come on. Still nothing? Just jump around until I can see it. Okay. All right. So I can see the image on the stream. I'm gonna just go with it. So okay, let's. I don't mind starting over. So we'll just try it again. Again, whatever we don't finish. So whatever we don't finish here together. Again, I just have to redirect you to my recorded videos. And again, I intend to. They should be the same because it's the same content. And I wouldn't really do anything that different. Versus being live in my pre-recorded video. So, and so I think the rhythm is we'll basically be doing one section a day. So today we'll just do the best we can with section 4.1, yada, yada, yada. Let me kind of get past this antiderivative. Okay. Okay, let's start here. So let me see. Versus being live in my pre-recorded video. So, and so, okay, it looks like it's still working. I'm gonna go with it. Okay. We have integrals and integration. All right. So antidifferentiating is often called integration. To indicate the antiderivative of x squared is x cubed over 3 plus c. We write the integral of x squared dx, this guy, is x cubed over 3 plus c, where the notation integral of f of x dx is used to represent the antiderivative of f of x. Okay. More generally, the integral of f of x dx is going to be the antiderivative of f plus some constant, where the antiderivative of f plus some constant is the general form of the antiderivative of f of x, right? So that's kind of a mouthful. I feel like when we start working an example or two, it'll start to clear. So the same way that we have like the techniques and properties for finding the derivative, we have similar techniques for finding the antiderivative, right? Let's see, what do we have? So determine these indefinite integrals, that is, find the antiderivative, right? So, we want to think of some f of x such that when we take the derivative, the answer is 8, right? So that integral is going to be what, just 8x plus some constant, right? Because the derivative of 8x is 8, which is what we wanted. The derivative of a constant is 0, so that guy is gone. So that should be it there. Okay, we're gonna go with this. So then for something like x squared, I think the way it goes is we add 1 to the exponent and divide by that new power, right? So x squared, if we add 1, is going to become x cubed. So we're going to have 3x cubed over 3 plus some constant. And then it simplifies down to x cubed plus a constant, right? And again, the way you check is by taking the derivative. The derivative of x cubed is 3x squared. And the derivative of a constant, this guy goes to 0. Okay, so we can be confident there. Okay, e to the x is its own derivative. So this one should just be e to the x plus some constant. And again, we check by, if you take the derivative, you should get that part that's in the integral. Let me see. I think that one is what? Natural log? Natural log of x plus some constant? Because the derivative of ln is dx by x. Okay, I feel good about these results. You see the first one here. Here's the next one. We got that one. I think we got all of these. And again, notice it, they're checking by taking the derivative. Okay. All right. So basic integration formulas, right? So these are some of the techniques, right? Whenever we integrate a constant, the integral of a constant is just going to be a constant times x plus c, or that k times x plus c. All right. So, just, because when you take the derivative, if like this with 3x, and the derivative of 3x is just going to be what? Just 3. Or, some number times x, the derivative is just going to be that number. If you have x to a power, right, then the integral of that guy is going to be, basically you add 1 to the power and divide by that new power plus your c. This was like where we integrated x squared. We had like 3x squared. We added 1 to the power and divided by that new power. So then, we ended up with x cubed. And again, provided that r is not -1. To integrate a power of x other than -1, increase the power by 1 and divide by the increased power. If it's to the power of -1, then we're talking about natural log, right? So if we have x to the power of -1, it's going to look like this. That's really just the log of x, the natural log of x, right? If x is positive, it's just natural log. If x is negative, we have to say the natural log of absolute value of x plus c. Because we cannot take the log of negative numbers, so we have to force x to be positive, right? By introducing the absolute value. But generally, we assume that x is positive, and more often than not, it'll look like the above case. Okay. So in example 4, in part 4, we have b times e to the power of ax. So the b kind of just persists out in front, and you have to divide by that a, right? So b over a e to the ax plus c, right? Okay. I feel like these become more clear when we work examples. Okay. So let's work in an example 2. Let me check on you guys' Zoom. I think it's okay. Hopefully it doesn't like go haywire. You guys look good. Okay, let's keep going. So use the power rule of antidifferentiation to determine these indefinite intervals. Okay, so for part A, right? Remember, all we're doing is trying to work backwards. Sometimes you kind of do like a guess and check. Sometimes you just use the rules that we just talked about, and you kind of keep going back and forth until you get an antiderivative. And again, you know you got it when you take the derivative, you get back to your original, right? So this guy, okay, so for part A, if we add 1 to the power, that's going to be x to the power of 8 over 8 plus some constant. And again, if you check by taking the derivative, right, if the 8 comes down, they're going to cancel, and then it's going to be to the power of 7. And then the derivative of a constant is 0, right? So we can be confident in this result. Okay. So then for B, same deal, right? Add 1. If we add 1 to the power, that's going to be x to the power of 100 divided by 100 plus some constant. So for square root, let's see. So square root is the same as what? X to the power of a half. Let's just try the same technique and see if it works. So then if we add 1, 1/2 plus 1 is 3/2. So that's going to be x to the power of 3/2 over 3/2 plus some constant. Okay. I mean, you could simplify that. You know, you could say x times the square root of x, or 2/3 x times the square root of x. I'm just going to leave it like this for now. I mean, we'll match it to however the notes prepared it, right? So then this guy, we have 1 over x cubed. We can rewrite it as x to the power of -3. Stop. We can rewrite this as x to the power of -3. So then if we use the same technique, add 1 to the power, it's going to become x to the power of -2 over -2 plus some constant. Okay. You know, and we could simplify that. That would be a -1 over 2x squared, right? There'll be a -1 over 2x squared. Okay, let's just go with this for now. So for A, I think we got this. X to the 8 over 8 plus a constant. Okay, for B, right here, x to the 100 over 100 plus a constant. For C, right here, right? So I think we left it as divided by 3/2. But when you say divided by 3/2, it's the same as you flip and multiply, so 2/3, right? Divided by 3/2 is the same as multiplying by 2/3, right? So we got that one. And then for D, right here, right? I think we said this. We didn't write it, but we said it. You know, the main thing is that we're getting the concept here. Okay. If anything is not clear, just feel free to unmute yourself to get my attention and we can talk about it. Okay. All right, let's try to work some more examples. So the quick check I usually leave as an exercise. Let's look at this one. So we're asked to determine the indefinite integral. Okay, right? Let me start by getting a copy of the original. So we have the integral of e to the 4x dx, okay? So e is its own integral, but remember we have to divide by that a, right? So it's still the e to the 4x is gonna persist, but we need to say divided by 4 plus a constant, right? And again, you check by taking the derivative. The derivative of e is itself, but then we have to say times the derivative of the power. So we're going to say times 4. The 4s are going to cancel, and we're going to finish with our desired result. Okay. Yeah, it looks good. I still see movement. Okay. Okay. Here's a type version, right? So as an initial guess, you might try this e to the 4, but when you take the derivative, there's an extra 4 there, right? So if we didn't divide by that 4, then we would have an extra 4. So they had to make an adjustment, and they modified the guess by basically dividing by 4 like we did, and then it worked out, right? So what they kind of did was a guess and check, right? But that's how it goes sometimes. You just try something, you check it. If it doesn't work, you got to adjust. Find each oh no, we didn't want the results. Oh, that's a quick check. Okay, it doesn't matter. Yeah, quick check. Okay. So theorem 3. So we have these properties of antidifferentiation. Property 1. So the integral of a constant times your function, dx, is going to be the constant times the integral. So in other words, the integral of a constant times the function is the constant times the integral, right? So when you integrate, you got a constant in there like that, you can just move it to the front. And then that way you have less that you're trying to manipulate while you integrate. That was a mouthful. The integral of a sum or difference is the sum or difference of the integrals, right? So if you take the integral of a sum, you can break it apart into 2 separate integrals. And an analogous is true for difference, for a subtraction, right? Okay. Let's keep going. Determine these indefinite integrals, assume that x is positive, okay. So I'm not going to write out those properties. I'm just going to apply the properties, right? Because, we're integrating this trinomial. We could break this into 3 separate integrals. And then every time we have a constant, you can actually move those constants in front of the integral. So this is really just the integral of x to the 5th, right? And then you just got to account for that 3. This is really just the integral of x squared. Just keep the 7 in front, right? Okay. But again, I'm not going to write out those properties exclusively. I'm just going to kind of write the result, right? So if I focus on that first term, the x to the 5th becomes x to the power 6 over 6. And again, that 3 persists. So that way the 3 and the 6 are going to cancel each other. Okay, the 7 persists. X squared is going to become x cubed over 3. Okay, and we'll make some adjustments there. And then the integral of a constant is going to be 8x, and then plus a constant. Okay, and then if we simplify, we get x to the 6 over 2 plus 7x cubed over 3 plus 8x plus a constant. Okay, and again, if we want to check if this is correct, we take the derivative. If we take the derivative, the 6 comes down, becomes a 5, and we get a 3 in front. That's exactly what we want. With the next term, if we take the derivative, the 3 comes down, they're going to cancel, and we're going to have 7x squared. That's exactly what we want. The derivative of 8x is 8, and the derivative of a constant is 0. Okay? Okay. So that was the first one. Okay, let's see, what do we have? Okay, so for this one, I'm tempted to distribute since we're dividing by monomial. In other words, since we're dividing by one term, we can distribute this term into each term in the numerator, right? So we can rewrite this guy in the following way. We're going to have 4 over x plus 3 plus 2x cubed dx, right? So when we integrate, I think the first one is what? 4 times the natural log of x. So 4 ln of x. The integral of 3 is going to be 3x. If we add 1 to x cubed, it's going to be what? X to the 4 over 4. So it's going to be x to the 4 over 2 plus some constant. Okay. So again, if you were to check, the derivative of the derivative of ln is going to be 1 over x, so it becomes 4 over x. You got that here. The derivative of 3x is 3. The derivative of x to the 4 over 2, the 4 comes down, so then you get what? 2x cubed, that's exactly what we want, and the derivative of a constant is 0. And then you could factor out an x. You can get a common denominator, combine like terms, and you'll get this guy here. Okay. So far, we're okay. Nothing too These can get challenging, but for right now, let's just savor this rhythm. All right. Let me check on you guys in Zoom. I'm just glad we were able to finally get going. You guys are looking good. Okay. Let's keep going. X to the 6. Yep. We got that one. That looks good as well. All right. I think they use the same technique that we did. Okay. So quick check and example 5. So find a function f such that f prime is x squared and f of -1 is 2. Okay. So basically they're asking us to integrate, right? So take the integral of x squared dx. Okay. So then that's going to give us what? X cubed over 3 plus some constant, right? So right now our f of x is x cubed over 3 plus a constant. But they also give us an additional piece of information saying when x is -1, the corresponding y is 2. So let's account for that. So when x is -1, we're going to get -1 cubed over 3 plus a constant, and the corresponding y is 2. I'll continue working over here. So then if we add 1/3 to both sides, c equals 2 plus a third is what? 7/3. Right? So then if we put all this together, our f of x should be x cubed over 3 plus 7 over 3. Okay. And we can check, right? Again, when we take the derivative, the 3 comes down, they're going to cancel, and we're going to be left with x squared, which is what we want. And the derivative of a constant is 0. That's clear. And then also what needs to be the case is when x is -1, the corresponding y should be 2. So then we get a -1 cubed is -1. So then -1/3 plus 7/3 is going to be 6/3, which is 2, right? So we were able to get both of the conditions. So this is our f of x. Okay, let's keep going. Yeah, right. So first we integrated x squared. We got the x cubed over 3 plus c. Then plugged in those conditions, and they got the same thing that we got using the same technique. Okay. I'm just grateful that we were at least able to stream because I don't like to not be available like that. Like I do the best I can to try to have the stream going before class, but today was just one of those days. Like it just would not work. It took me 10 minutes to log in, how I log in every day. I don't know why today it just want to be like, this is your first time logging in. I was like, no, it's not. But I mean, that's how it goes. And so again, the backup is whatever time we lose together, I have to rely on my pre-recorded lectures. Like that's why I made it, because a lot of times this stuff is just unavoidable. Like you can't stop it. You know what I mean? You can't. It's not like just showing up to a board and writing. Even then, being in person, it's still you got to get there. Between the potholes in the city, or oversleeping, or low energy. So you know how that goes. You just do your best, forget the rest, don't stress, and be blessed. Okay. All right, let's see. Oh, no. Okay. So we have a solid 25 minutes. Okay. So with that, what I would like to do, let's go ahead and kind of look at some of the homework. Now, I can go through homework for 4.1. If you guys want to go through other questions, like questions from other sections like chapter 3, we can do that as well. So let me change my view to seamless. And let me add a page right here. Okay, looks good. Okay, yeah, we'll work with that. Okay, so I want to work there. No, let's just work here. We should be good. Wow. I guess I just have to get started earlier. I thought 15 minutes would be enough time to get set up. Boy, was I wrong today. So I guess I need to start getting the thing 30 minutes early. I thought 15 was enough, but I guess next time I'll just start 30 minutes early. until it works. I'd rather just be waiting on you guys. That's what I'm trying to do, but every time I think I give myself enough time, the universe is like, it just laughs at me. It throws me all these curveballs. It tries to frustrate me. And then I have to laugh just so I don't lose my mind. Okay, calculus. All right, come on. So let's go to chapter 4. Allow. I can still see my stream, so we're good to go there. Where is it? Okay, right here. Okay, let's work on anti-differentiation. Week 10. Captain's log, day 17. Today, we're working on 4.1 anti-differentiation. I don't even know if y'all know that reference, right? I'm so tempted to offer something if y'all can get that reference. I can't say that I will offer something, but I'm just curious if y'all get that reference. When I say captain's log, this is day, yada, yada, yada. Anyway, okay. This is a review, so I'm going to skip this one. I want to get to chapter 4. That's chapter 2. That's chapter 3. We're almost there. Let's keep going. Let's get to something we talked about today. There we go. Okay, so this comes from chapter 4. This is question 6 from the corresponding homework. So find the integral, right? We got a constant. So the integral of a constant is just going to be that constant times, let's see, let's go like this, off, okay, right here. It should just, I'm going to say 10x plus c, 10x plus, let's do a capital C. Awesome sauce. Next question. Okay, right, power rule. So we add 1 to the power and divide by the new power. So x to the power of what, 9 divided by 9 plus the constant. Okay, that's pretty much what we've been doing all day. Let's do the same thing here, right? If we add 1 to the power, that's going to be what? X to the 7 over 2. So I'm going to write it like this. X to the power of 7 over 2. I'm going to say divided by. Well, if we divide by 7 over 2, that's the same as multiplying by 2 over 7. So I'll put my 7 here, and I'll put a 2 here, and then we'll say plus a constant. Okay. Again, if anything isn't clear, just stop me. Let's keep going. Yeah, we're moving and grooving. I'm glad we're able to do this, because this is what I've been wanting to do. I've really been wanting to have some time to go through the homework. And I have at least one student that, like, man, he be pushing me to my limit. It'd be good, though. It'd be good questions. It'd be making me think. And, you know, sometimes I have to dig a little bit to get to the bottom of it. But I'm glad that we have those times. So, because, like, if you guys don't ask questions, I really don't have a sense of what you're experiencing. But when you start asking questions, like, okay, you know, that gives me a little bit of context, you know. And I do acknowledge that some of the questions are kind of bizarre. And so because of that, and just the nature of it being remote and its technology, again, my compromise is unlimited attempts with minimal late penalty, right? So as long as you're willing to keep trying, you can improve your score all the way up until an A-, no matter, all the way up until the very end of the semester. Okay, let's apply the properties or techniques that we talked about, right? So that first term is going to become what? X to the power of 3 over 3, right? Divided by 3. Okay, that's not a 3. Okay, nope, that's not a 3 either. There we go. What is that going to be? Minus 5x squared over 2. Over 2, okay. Plus what? 2x. 2x. Plus a constant. Oh, let's do a capital C. Okay. Okay, so this one I would rewrite as a negative exponent first, right? So this is really the integral of x to the negative 4. Then when you add 1, it becomes x to the negative 3, right? So x to the -3 over -3 ultimately is going to become -1 over x to the power of 3. 3 times that, right? Because it's x to the -3 over -3 plus a constant. Okay. We are moving and grooving. Shaking and baking. I need one more. I can't think of another one. Okay, right? Same technique here. We got the square root of x to the 11. We can rewrite it as what? X to the power of 11 over 2. So then when we add 1 to the power, that's going to be x to the power of 13 over 2. Right? So x to the power of 13 over 2 is going to become what? 2, that's not a 2. 2 times the square root of x to the power of 13 over 13. I think that's it. Because we have x to the power of 13 over 2 over 13 over 2, right? So then if you flip and multiply, and then we got to say plus a constant. Okay, let's just keep going. We still have a solid 10 minutes. Find all antiderivatives of the following function. Okay, so e is its own antiderivative, so we're going to at least go ahead and capture the e to the power of -17x. But then the added caveat is that we need to say divided by that -17, and then we're going to say plus a constant. Okay, next question. Let's do the same thing here, right? So whenever we're saying a constant times our function, the constant can just kind of sit out in front. So we're going to do that. We're going to, e is its own antiderivative. So we're just going to go ahead and capture that, -0.1x. But then the added caveat there is that we have to divide by that a, which is -0.1. So what is that? 1 over 10, so times 10. So it's really a -60 on top. Oh, it's probably going to make me retype all of this. No, that's not what I want to do. How do I undo that? Shyster. Can I cut that? If I can cut it, that will work. Okay, I think we might be in business. Paste. God is good, right? Plus C. Okay. So again, the 6 persisted. I just wrote E. I just rewrote E, but then I divided by a -0.1. So dividing by -0.1 made the whole thing negative. Dividing by 0.1 is the same as multiplying by 10, and then plus our constant. Okay. So hopefully this isn't too bad for you guys. I know, I'm pretty sure you guys are exhausted. I know this stuff is challenging. I try to give you guys a way out. I can't make you do it. I can't do it for you. I can just try to encourage you and, help you and position you for success and stuff like that. Okay, find the integral. Okay, so if we focus on that first term, 3x is going to become what? 3x squared over 2. So then 3x squared over 2. Okay, the second term, wait a minute. I didn't see that square. We do need to expand. Okay, so I'm going to take some notes here. Let's see, can I do integral? Oh, wow, I didn't know I could do that. Yes.
From the last question, how'd you get a -60 again?
Okay, let me finish this one and then I'll go back. The -60, because remember with E, when you take the integral of E, it's going to be itself, but then you have to divide by the A being the coefficient of the x in the power. So the coefficient of the x in the power was the -0.1, so I had to divide by -0.1. So dividing by -0.1 made the whole thing negative, and then dividing by 0.1 is the same as multiplying by 10. So 6 times the -10 gave me the -60. Okay. If we expand this binomial, we're going to get what? 9x squared. Okay. 10 times 3 is 30. So plus 30x plus 25. Okay. Thank you. Stop. Okay. There is a dx there, but I'm just going to ignore it for right now. I'm just taking notes here. Okay. So now in this form, let me just put the dx because I don't want you guys to make a habit of not writing the dx. Even we're just taking notes. I'm just typing the notes instead of writing it out, right? Okay. So now when we go to take the integral, it's going to be x cubed over 3. So I think that gives us 3x cubed. So 3x to the power of 3. That's going to be 30x squared over 2 becomes 15x squared. Okay. And then plus 25x plus a constant. Let me get rid of these notes. Okay. So if you take the derivative, oh, well, I'm just going to go with it for now. Okay. See what else we got. Use the form this to solve the following. Okay. So it says, okay, yeah. So, right. If you think, so this is like e to the x. Okay. So the same rule applies as if we were taking the integral of e to the x, but the only additional thing that we need to add is we need to divide by the natural log of a. Okay. So in this case, there's no coefficient in that power, so we can ignore that part. But we need to say 1 over the natural log of 14, right? Because if instead of being base 14, if they were base e, then that would just be a 1 and you wouldn't even notice it. And then we still keep our 14 to the power of x plus a constant. Capital C. Okay. So again, they gave us the form on how to approach that one in the instructions. The answers can be determined by rules, but some algebra may be required beforehand. Okay. So with this, I would rewrite it, right? So because we're divided by a monomial, we could distribute it. I'm going to rewrite this. So u to the 7 is going to become u cubed, u to the power of 3. Those are going to cancel, so we're going to say minus 3. And then we're going to say plus 5u to the power of negative 4. Okay. Let me just do like this. All I'm doing right now is basically taking notes, and before we haven't taken the integral yet. So, and just basically rewriting the original and take some notes. So then now when we go to take the integral, u cubed is going to become what? U to the 4 over 4. So u to the power of 4 over 4. Okay. So the integral of negative 3 is going to be negative 3u. Okay. And then with that last one, if you add 1 to the power, that's going to be u to the negative 3 over negative 3. So it's going to be a negative 5u to the, or actually negative 5 over three u to the power of 3, right? Because again, that was u to the negative 3 over negative 3. The negative is there, the 3 is there, the u to the negative 3 is there, and the 5 is there. And then we're going to say plus a constant. Oh, and let me get rid of my notes before I hit enter because it's going to mark it wrong. So I'm going to get rid of this. Okay. I think we're okay. Let's go with that. We got time for maybe 1 or 2 more. So this one I would use, you can use like synthetic division or polynomial long division. Let me see if I can do synthetic division. If I was rewriting this and writing my answers with synthetic division, I would need to write it out. We could factor because that's sum of cubes, right? 4 times 4 is 16. So, okay, if we factor the numerator using sum of cubes, the x plus 4s are going to cancel. I'm going to take my notes here. So then, let me think about it. It's going to be what? X squared plus what? 4x plus 16, right? That's what's left over after you cancel. It should be dx, just for the sake of time. I'm just going to go with this. So then if we actually integrate, we're going to get x to the power of 3 over 3. Okay. Plus what? 4x, x squared over 2 gives us 2x squared. So plus 2x squared. And then plus 16x. Plus 16x plus a constant. Okay. Let me check real quick. So then x cubed over 3, when we take the derivative, becomes x squared, okay? 2x squared, when we take the derivative, becomes 4x, okay? The derivative of 16x is 16, and the derivative of a constant is 0. So then we can get rid of all of this stuff.
Professor?
Yes.
I was wondering, how'd you get the
Well,
integral x squared?
wait. My factoring right here is supposed to be what? Negative there? Let me think. Hang on. Let me just make sure this is correct. All right. Okay. So you had a question?
Yeah, I was wondering, how'd you get the integral x squared plus 4x plus 16?
Okay. Let me take some notes on this one. So I'll get a screenshot. Let's see. This is decent. Screenshot. We're going to copy and delete. You can paste it right here. I want to cut. Word at the last. Paste. Okay. All right. So the first part is factoring that numerator. So that comes from before college algebra. Factoring, right? I guess I'll just do it in black. So we have this x cubed plus 64. That's the sum of cubes, right? So I use this technique called the chair method for factoring sum of cubes, right? So we want to factor this guy. So to do sum of cubes, first I use this thing called Biggie Smalls, right? So we do a small set of parentheses and a large set of parentheses. Okay, so then we need to do our signs. I think this makes the plus sandwich, right? When that's a plus, this first sign matches that one. The last sign is always plus, and then this second sign is always the opposite of the first one. All right, so I call this a plus sandwich, right? Again, let me recap that. This always matches this, okay? The last one is always plus, and then this one is always the opposite of this guy. Right? Okay. So the chair part comes in here. So this is sum of cubes, right? So then this I rewrite it in the following way. X and 4, x and 4, x and 4. Because x cubed is x times x times x. 64 is 4 times 4 times 4, right? So then the chair comes in here. So this is the first part. I'm just going to label it as a 1. And that means put an X and a 4 there. And actually, let me stop. Let's do this, and we'll do that part in blue. Okay. So then the next part is the left part here. I guess I'll do that in purple. All right, that's the second part. And again, the blue was here. Style. Okay. So then the second part, X times X is X squared. Let's do orange. The third part, X times 4 is 4X. And I guess I'll do green. Then the fourth part right here, 4 times 4 is 16. So that's where that came from. It was factoring a sum of cubes, and that's something from before college algebra. Factoring. All right, so I think I do have an entire handout. I have an entire chapter devoted to factoring. It should be in our handout section, and there's also a factoring summary, how to approach a factoring problem. So if you need practice on factoring, it's actually in our handout section on Blackboard. Okay, but that's it. But this is where that came from, right there. All right. So then I think you can take it from there. That was the most challenging part of that one. Okay. Any questions, guys? I feel like there should be questions. Okay, if there aren't any burning questions, we're going to go ahead and end the session here. Let me make a copy of this available for you. So I'm going to send it to the box, the proper folder. Go ahead.
We have some questions over section 3.5.
Okay, let me send this here, handwritten. Okay, I think we're good. Let's send it there. Okay. So when this bar finishes loading, you'll get a copy of anything that you saw me writing. I think we're going to kind of keep working, but if you have to go, we are officially ended the session here. And from one beautiful mind to another, enjoy your rest of your day. Again, you're welcome to stay as we go through these other questions. Okay, guys? Take care. Peace. Mr. Lowe, with the questions, just use the Ask My Instructor. That's the best way. Just resend it, or, that's the best way. Just let me know once you've sent it. Good job. Oh. I'm glad we got the stream going. I was feeling some way. And yeah, I don't know what's causing that. And I just have to kind of keep trying until it works. And it's not consistent. Like sometimes one thing works, sometimes another thing. It's just you have to kind of keep trying until it works. Because I can go ahead and open my email. Let's see right here.
I sent one question.
Okay. Okay, right here. So, you sent a few of them. Okay. Let's start with this one. Let's see. It says a normal window is a rectangle. I think this one might be a little bit funky. Let me go like this. Yeah, right there. Okay. Let's do it again. Okay. So this comes from section 3.5, question 56. It says a normal window is a rectangle with a semicircle on top. Suppose that the perimeter of a particular normal window is to be 24 feet. What should be the dimensions in order to allow the maximum amount of light to enter through the window? So we have our perimeter, and it sounds like we want to maximize the area, right? Let's see. Okay. All right. Let me get a copy of this guy. And I guess I'll keep there, here. Here, this is what I'm looking for. Let me copy and delete. Let's paste. Okay. So what we could do is find the area of each simple figure and then just add them together, all right? So let's start with the rectangle. Area of a rectangle is length times width. So we're gonna see, can we find the area in terms of X? Right now, so the area of the rectangle is gonna be what? Y times 2X, right? So the rectangle, basically the area of the window is gonna be the area of the rectangle plus the area of the semicircle. All right. So then the area of the rectangle is going to be what? Y times, or 2X times Y. Let me just write it as 2XY. That's the rectangle. And the area of a circle usually is pi r squared. So I'm going to capture that, pi r squared. But we have half the circle. So we're going to say over 2. Okay. And in this case, the r is going to be X. Okay. Okay, so for right now, again, our goal is to maximize our area. We want to get the area based on X. And right now our area is 2XY plus pi X squared over 2. But they gave us additional information that the perimeter is 24 feet. Okay. So the perimeter of this figure, we're going to say, let's see if we get it in terms of X. Let me see, Y plus Y. So 2Y plus 2X, right? So 2Y plus 2X. Circumference of a circle is pi times diameter. So 2 pi X, but then we don't have the whole circle, so it's just pi times X. Again, normally the circumference in this case will be pi times the diameter, so 2 pi X, but we only have half the circle, so we got to cut that in half. So then it's just going to be pi times X. And it says that the perimeter is equal to 24 feet. Okay. So then what we want to do is get Y in terms of X and then plug that Y into the area. So that way we can get area only in terms of X. Okay. So if we solve for Y from the perimeter, we get 2Y equals 24 minus 2X minus pi X. Okay. Divide everything by 2. Y equals 12 minus X minus pi over 2 times x, right? You could combine like terms there, but this is good enough, right? So now we got y in terms of x, so let's plug this into our area formula. So again, our goal is to maximize the area. We do want to write it in terms of x, and that's going to be 2x, and our y is 12 minus x minus pi over 2 times x plus pi x squared over 2. Okay, hopefully this is okay up until now. Let me expand and simplify, combine like terms. So then if we distribute, we're going to get what? 24x minus 2x squared. So minus pi x squared plus pi x squared over 2. So what is that? Negative 2 over 2 minus 1 over 2 is a negative 1 over 2, right? Again, our goal is to maximize our area. And if we combine like terms, we got this 24x minus 2x squared. 2 over 2, negative 2 over 2 plus 1 over 2 is a negative 1 over 2. So then it's just going to be a negative pi x squared over 2. Okay. So now we have the area in terms of x alone. Now, if we want to maximize it, now we're going to take the derivative, set it to 0, confirm that it's indeed a maximum, all that kind of jazz, right? So we need to look at a prime of x. So then it's going to be 24 minus 4x. The 2 comes down, minus pi x. Okay. We want to set this as 0 and solve for x. So I'm going to move those terms with x's to the right-hand side. So if we add those to the right, or, I'm going to add them to the other side. I'm also going to go ahead and factor. So we're going to get what? 4 plus pi times x equals 24. I added my 4x, I added my pi x, factored out my x. We get this, right? So then long story short, x equals 4 plus pi under 24. That's the exact result for x, right? So that x, so we need to confirm whether that's a maximum or not. I need to find that number. Right here. Let's do this one. Okay. So then 24 divided by 4 plus pi. Like this, okay. So that's about 3.3, right? You could say 3.36, right? This is approximately 3.36. So then if we put this on the number line, here's our 3.36. So if we choose a number to the left and plug it in the derivative, I'm going to choose 0. If I plug in 0, this goes to 0, this goes to 0, we get a positive result. All right, that's a good omen. So so as far as A prime is concerned, again, this is our 0. To the left of that guy, I plugged in when x was 0, we got a positive result. So that implies that our original function is increasing. To the right of this would be something like 4, right? If we plug in 4 into our derivative, that's going to be a negative 16. That's going to be like a negative 12. It should be negative, right? Negative 16 minus 12 is larger than this guy. So that result should be negative. So on the right of this guy, when we plug it into the derivative, we get a negative result. So that means our original function should be decreasing. That confirms that this is indeed a max, which is what we wanted to confirm. Okay. So then this X, so the max occurs at this X. The question said, what should its dimensions be in order to allow the maximum area? So we got our X. Again, the X that we got was this guy here. And then we just need to find the corresponding Y right here. We can use this. Copy. Okay, so then Y is 12 minus that X minus pi over 2 times that X. So we just need to crunch the number. So I think what I'm going to do right here, I'm going to go to Y equals, and I'm going to just put in 12 minus X minus pi over 2. Let me put that pi over 2 in parentheses. Okay. So then I just want to call on that function. So I'm going to go to variables. And I want to plug in that answer, that above answer, to get my Y. Oh, it's the exact same. Okay. So it looks like they're both the same number. Okay, let's see. Let's see, what does it say? Okay. Here. Other maximum, it says do not round it to the final, then round to 2 decimal places. So 3.36. Okay. 3.36. The radius, both of them are 3.36. 3.36, that's not a point. Feet. And the height. Okay. Did you have any questions there? You might be muted. I don't know if you're saying anything.
No, sir.
So seamless. Okay, so that was that one. Let me highlight the final result here. Okay. So then the next one is this one. Okay, let's go like this right here. Oh, let me plug this thing in. The battery's getting low. Okay. So it says a power line is to be constructed from a power station at point A. Where's A? Okay, I see A. To an island at point C, which is 2 miles directly out of the water from at a point B on the shore. Okay. So it looks like we're trying to find the hypotenuse. It costs $3,600 per mile to lay the power line underwater and $2,000 per mile to lay it under the ground. Oh, I see. So part of it's underground and part of it's underwater. Okay. At what point S, downshore from A, should the line come to the shore in order to minimize the cost. Note the S could very well be B or A hint. The length of CS is there. Okay. Okay. This is doable, right? We're going to be minimizing the cost. So we need to find a cost function in terms of X, right? Let's get a copy. Because once we get our cost function, then we're going to minimize by taking the derivative, yada, yada, yada. Let me get it from here. Copy and delete. I'm going to paste it here. Okay. So let's see. Now, when we go to write this cost function, right, you have the part that's underwater plus the part that's underground, all right? So our cost function is going to come from the part that's underwater plus the part that's underground. Okay. So then if we focus on the part that's underwater, that's the red line, CS. So they gave us that one, so we're just going to use it for the sake of simplicity. Since they gave it to us, 4 plus X squared, okay? Let me see. That's the distance, right? And it says underwater it costs 3,600 per mile. So then we're going to say, so the part that's underwater, we're going to say 3,600 times the square root of 4 plus X squared, right? We have the length times the cost per mile plus the cost per mile underground is going to be $2,000 per mile, so $2,000. And the length underground, it looks like it's 4 minus X. Okay. So we're going to put 4 minus X. Okay, so this looks like a good cost function, right? Because we have the cost. This should tell us the cost, and it's only in terms of X. So now our goal, we want to minimize the cost, right? We want to minimize our cost function. So basically what? We take the derivative, set it to 0, and confirm that our number is indeed a minimum. All right, so then C prime. Okay, so the 1/2 comes down, what is it, 1,800? You're going to have this 4 plus X squared to the power of a negative 1/2, and then times what, 2X. Okay, that's the first term. Second term, if we distribute, the first one is gone. So it's just going to be minus 2,000. Because if we distribute this 2,000, that's going to give us 8,000. The derivative of 8,000 is 0. The derivative of negative 2,000x is just going to be negative 2,000. Okay. So then the goal here, we want to set it to 0 and solve. I'm going to get a common denominator, right? So we have this 4 plus X squared. That's under the radical. And on top, it looks like we have 3,600. 3,600x. Okay. Okay. So we got this minus 2,000. If I want to get a common denominator, I'm going to multiply by 1 in the form of square root of 4 plus X squared over square root of 4 plus X squared. Okay. I'm just multiplying by 1 so I can get a common denominator equals 0. Okay. So then if we keep going, we got this 3,600x minus 2,000 times the square root of this 4 plus X squared. Okay. And on bottom, we just have this 4 plus X squared like this equals 0. Okay. So then to solve, we're going to find any x that makes either the numerator or the denominator 0. All right. So if we set each one to 0 and solve, okay, this numerator. So then we get 3600x minus 2000 times the square root of 4 plus x squared. We're going to set that equal to 0. And also the other one is square root of, actually, if you square, you get 0. I think the denominator won't ever be 0 because if you put in -2, you get a positive. So we can't get the denominator to 0. So we only have to get the numerator. Okay, so it's just the numerator in this case. Okay. So usually when you're solving for a square root function, you got to isolate the square root. Okay. So I'm going to add that 2000 square root and, and divide. I'm actually going to go ahead and divide both sides by 2000 as well. I'm isolating the square root. So then I get square root of 4 plus x squared. Let's see, 36 over 20, 1.8. Let me do this. I'll do 36x over 20. We can divide both of those by 4. 9x over 5, okay? So now once you get it here, you square both sides. So if we square both sides, and I'll just show it here, squared and squared, then we get, on the left, we get 4 plus x squared. On the right, we get 81x squared over 25. I think at this point we can set the 0. So I'm going to move everything to the right. If we subtract everything, will it help us? Because that's going to give us 80. Man, that's throwing things off.
Yeah, Professor.
Hmm.
How'd you get the 36x over 20?
I added the 2000 square root of x on both sides and then divided both sides by 2000.
Oh, okay.
Guess we just need to keep going. We could use, if I subtract 1, let me see. So minus 20 would be 61, 60, 56. I think it's 56, right? Hey Siri, what's 81 minus 25?
81 minus 25 is 56.
Okay. So then we'll get 56x squared over 25. I guess we can leave it as equal to 4, okay? If we multiply by the reciprocal, x squared equals 100 divided by 56. Oh, it's almost a perfect square. 28. So then x equals, what's our context here? We're not going to take the minus because the minus doesn't make sense in the context. Square root. So it's going to be square root of 100 is 10 over 56 is what? 27? Nope, 28. 28 times 2. So that's 4. 9 times 4, right? No. 12. I think it's let me see something. So 56. It's 2 times what? 28. But 28 is 2 times 14, so it's 49, 56. So then 8 times 7, right? So then the square root of 8 is going to be 2 times the square root of 14. Okay, so that's the exact result. Okay. So let's go back and answer the question. S. So we're trying to solve for S. At what point S from A should the shoreline in order minimize the cost? Okay. So then 4 minus X. So then S is going to be 4 minus that answer. Actually, you can write it as 5 over the square root of 14. Okay. And then I think we got to use our calculator from there. Okay. Looks like it's 2.66. I think it's miles. We got 2.66 miles. Oh, now we need to confirm that this is indeed a minimum, right? Okay. So if we look at our positive X, here's the 2.66. We want to, did we take the derivative? I hope we did. Yeah. So our derivative is there, okay?
Oh, hey, sir.
Yes.
How would you get the 56x squared over 25 equals 4?
Oh, because the original asked us to solve for S, and S is going to be how far down from A we are, right? So S is this guy right here. So that's where I got the 4 minus X from.
Oh, okay.
Let me make sure that this is correct though. Okay. So a number to the left, if we plug in 0, that's going to be a 2 on the bottom. The whole thing collapses to 0. Maybe we shouldn't use 0. Let me go back. Oh. Are we missing something? Maybe we should have used plus or minus. Because it looks like, but 0 still doesn't. I mean, it could be A. I think 0 is one of our choices. Because I probably should have used the plus or minus. Let me see if I do 0. No, it's a 2. No, that doesn't work. But I think there might be another result. I feel like I need to go back and use plus or minus. Oh, no. We're good. I was missing the 2000. Okay. I think we're okay. So when we plug in 0, we get a negative result, right? Because this guy collapses to 0 and then the negative 2000 persists. So that means that everything to the left of this is negative, which means the original function is decreasing. A number to the right, like if we plug in 3, this is going to be positive down here. This is positive. I'm pretty sure that this is going to be larger than 2000. So a positive minus 2000, a positive number larger than 2000 minus 2000 ultimately is going to be positive. I'm just kind of assuming it right now. Right. Again, that would confirm that this is a minimum. And I think we can stand by that result. Okay, let's go check. We got well, that was an adventure. It was a true adventure. Okay. All right, let's pull up the next one. Let's see. right here. That's a repeat, which is good. Oh, wait a minute. Homing pigeons avoid flying over water. Suppose a homing pigeon is released on an island which is 5 miles away from point B. Point B is 12 miles downshore. Assuming the pigeon uses energy at a rate of this towards the point S. Oh, that's interesting. Okay, we're gonna give this one a try. It's very similar to what we did, but I can see where there are nuances that are different as far as the work. So we're gonna take a look at it. Of course, you're gonna pop up over there. Let me get rid of that. Get rid of this and this. Let's try that again. So this one is similar to the one that we did, but it is a little different. So that's why I'm kind of working on it. It says homing pigeons avoid flying over water. Suppose a homing pigeon is released on an island at a point C, which is 5 miles directly out in the water from a point B on the shore. Whew. Point B is 12 miles downshore from the pigeon's home loft at point A. Assume that a pigeon flying over water uses energy at a rate of 1.26 times the rate over land. Towards what point S downshore from A should the pigeon fly in order to minimize the total energy required to get to the home loft at A? So the total energy is going to be the energy rate over water times the distance over water plus the energy rate over land times the distance over land. So I would imagine that they use more energy flying over water than over land. Over water uses energy at a rate of 1.2 times the rate over land. So I'm tempted to let the rate over land, oh, that's the distance. Okay, so I'm going to let the energy consumption rate over land, I'm thinking it's just going to be a 1, right? Just whatever his energy is. And then the energy consumption over water, I'm going to let that be 1.26 because it's 1.26 times the energy consumption. So they use a little bit more energy over water. The distance over water, I think we can use, I guess we can use Pythagorean theorem for the right triangle. So a squared plus b squared equals c squared. Okay, we'll get that momentarily. And the distance over land like is going to be 12 minus x. Okay, so let's take some notes here. Ooh, good chaka. Get a screenshot right here. This is fine. Let's copy and delete. Right here, let's paste. Okay, fortunately, they gave us a good amount of information, so a little bit of headache, right? So the total energy, we want to minimize the energy, right? So we're going to try to get the energy in terms of x. And again, the goal is that we want to minimize the energy. Okay. So the energy rate over water, I'm just going to let that be. I think it's just going to be 1.26 times the distance over water. So that's the hypotenuse, which is going to be what? The square root of 25 plus x squared, right? That's similar to what we had before. And again, I just use Pythagorean theorem for the right triangle here. 5 squared plus x squared, and I take the square root. Okay. So then plus, I'm going to let the energy rate over land, I'm just going to let that be 1, right? Whatever their energy is that they use. And then the distance over land, so will be 12 minus x. Okay. Okay. I think we're okay. So far we have, again, if our energy function is correct, and we do have it in terms of x alone, so we want to, can we expand this? No. So we want to minimize by taking the derivative, right? We want to take the derivative of this guy. So then E prime, it should still be working out. Let's see, why wouldn't be? So then E prime, so this 1.26 persists. For the square root, that 1/2 comes down. You still got this 25 plus x squared. Now it's to the power of a negative 1/2. But then we need to say times 2x. And then that second part is just what, minus 1. Right? Because the derivative of 12 goes to 0. The derivative of negative x is negative 1. Okay. So then from there, we want to set this to 0, combine like terms, and solve. Off the rip, I want to go ahead. This 2 cancels this 2. Okay. Okay. So then I'm going to rewrite this. We got this 25 plus x squared, and that's a square root. Okay. That's the only thing in the denominator. On top is this 1.26x. Now, if we say minus 1, that's going to be the same as, I'm going to rewrite that minus 1 as minus square root of 25 plus x squared over itself. Okay. Equals 0. Okay. So then we get 1.26x minus the square root of 25 plus x squared over the square root of 25 plus x squared equals 0. I think we have a similar argument where we can't get that denominator to be 0. Because if we try to plug in -5 is positive, +5 is positive. So we can't get the denominator to 0. So we're just going to focus on getting the numerator to 0. So then we're going to have this 1.26x minus the square root of 25 plus x squared, 0. Isolate your radical, we get the square root of 25 plus x squared equals 1.26x. Square both sides. 25 plus x squared equals 1.26 squared times x squared. All right, I'm leaving it like that for now. I'm gonna set this to 0 and solve. Let me just go ahead and find, let me square this thing. Let's do here, let's go full screen. We left off here. We want to bring our calculator back. Okay. Right there. Okay. Come on. Okay. So then weird, I want to say -1. 5876. Okay. equals 25, okay? So then x squared equals, and if we take the square root, again, normally we would do plus or minus, but x being a distance, it doesn't make sense to have a negative in this context. So it's going to be the square root of this. And let's just go a step further. Okay, so that's the exact result that we got. And then, you know, we use a calculator to crunch that number. Come on. Come on. Okay. So if we have x, then if we want s is going to be 12 minus x, right? So then s is going to be 12 minus that result, square root of the 76 under 5, right? Okay. So we're going to say 12 minus 5 divided by the square root of that answer. Okay. So we get 5.48 approximately. Is that miles? So let me see. Towards what point S downshore from A should the pigeon fly in order to minimize the total energy required to get to the home loft at A? So we got 5.48 miles. So hopefully, we still cross the fingers. All right. Sometimes we get this stuff wrong. All right, let's see. First express the distance in terms of x. Yeah. Express the total energy. Let me look at their example. I think it's with the energy thing. Let me check this. Yeah, it should be rounded to there. Mm-hmm. Yep. Square root of that. Okay. Maybe we got the energy consumption wrong. So let me view an example. Mm-hmm. So yeah, right there, right? The amount of energy is that. Okay, that's fine. So we got that set up properly. Maybe we just made an error somewhere. Let's just go back and check our work. Right here. But I think that's good. I think that matches what they had. Yeah. 6 minus x. Mm-hmm. Okay. So we take the derivative, right? The 1/2 comes down, 25 plus x squared times 2x, okay? That's minus 1. Those cancel. We get our 1.26x divided by the square root of 25 plus x squared minus 1 equals 0. Common denominator. That minus that. Mm-hmm. That looks good. So if you add that to both sides, square both sides, say you subtract that. So you did, it should be 1.26 squared minus 1. Maybe that's where I'm messing up. Okay, that shouldn't change. Let me put that in parentheses. 1.26 squared minus 1. 5876. Okay. Take the square root. You divide. So then it should be 5 over 0.5876. Okay. So then it should be 12 minus 5 over the square root. Let's see. 12 minus 5 divided by the square root, 0.5876. 5.48. Yeah, I don't know, because it feels like we did the same thing they did. Like I feel like we just made some kind of calculation error somewhere that we're missing. Let me see. All right. The above function is to be minimized. Critical, set it to 0. We got that minus 1. Yep. Rounded to 3 for double us is needed. Oh, 3 decimal places. Jesus. Oh man, reading is fundamental. 5.477, right? We will run to 2 decimal places. 5.477. You're gonna have to wait, buddy. Thank you. We just rounded to the wrong number of decimal places. So what we did more than likely is correct. Let me check one more time. Yeah, all right. I'm busy. No. What do you want? No, I'm busy. No, you're gonna have to wait. Yeah, we were just round to the wrong number of decimal places. I don't know if you had any questions there. I'm going to pull up the next one. We can go back and talk about whatever we need to talk about. Let's see. Okay. So then there's this one. Sure, let's take a look at it. Let's share right here. Nope. Let me just get rid of all of this. Try it again. Okay, so this one comes from 3.5, question 68. It says a road is to be built between 2 cities, C1 and C2. Okay, let me see. That's fine, I guess. Right. Which are on opposite sides of a river of uniform width R. Okay. C1 is A units from the river and C2 is B units from the river. Okay. Where A is less than or equal to B. A bridge will carry the traffic across the river. Where should the bridge be located in order to minimize the total distance between 2 cities? Give a general solution using the constants A, B, P, and R as shown in the figure. Okay, so our distance formula, right? We're trying to go from C1 to C2, the first city to the second city. So they're using basically right triangles, right? it looks like they filled everything in. We want to minimize that distance, so we need to find the hypotenuse from C1 to the water. We know the distance across the bridge is R, and then we find okay. So for instance, the distance from C1 to the water is going to be the square root of P minus X squared plus A squared, right? So you see it. Okay, I think it's D, right? Because the distance from C1 to the water basically is Pythagorean theorem. So square root of P minus X squared plus A squared, right? So that's the first part of D. And then plus the distance across the bridge was R, so there's a lone R there, plus the distance from the water to city 2. So again, Pythagorean theorem, square root of X squared plus B squared, and you see it there. So yeah, they basically just did the Pythagorean theorem twice plus the distance across the bridge. So I'm just going to go with D. Did that make sense?
Professor,
Sure.
they did what?
Yeah. So all we did was this image, right? I don't know. Right? We're trying to find the distance from city 1 to city 2. So we're basically going along that pink path. We want to minimize the distance. So all we're going to do is find the distance from C1 to the water. We're given that the distance across the bridge is R, and then we're going to find the distance from the water to city 2. Okay? So the distance from city 1 to the water, we're going to use Pythagorean theorem. A squared plus B squared equals C squared. So then the hypotenuse is going to be that P minus X squared plus A squared, and you take the square root of the whole thing. And you can see that captured in the first part of D. All right. So then, it needs to capture the distance across the bridge, which is just R. So in D, you see a lone R there. That's where that comes. And then the final distance is going to be the distance from the water to city 2. So again, Pythagorean theorem, that's going to be the square root of B squared plus X squared. And you see it there in part D. So part D had all three distances there together. All the others were missing a leg. So then that's why D was correct. Okay. And then this is gonna have to be the last one because I am burnt. And we'll just kind of keep going back and forth like next time. Let's try this one here. Okay. Let's see. So this one, let's can we make it bigger? That should work. Okay. So it says a store sells Q units of a product per year. It costs D dollars to store 1 unit. Oh, this is like the one. Okay. We did something similar to this. Let's see. A store sells Q units of a product per year. It costs D dollars to store 1 unit for a year. To reorder, there is a fixed cost of B dollars plus C dollars for each unit. How many times per year should the store reorder and in what lot size in order to minimize inventory costs? Use the general solution to find how many times per year a store should reorder and in what lot size. We did one like this, order size and lot size. Let me see. So basically we need an expression to a cost for the cost function, right? To store for the inventory costs. Let's see. There's a fixed cost of B dollars plus C dollars for each unit. Plus C dollars for each unit, right? How many times per year should the store reorder and in what lot size? So the order size and the lot size. Okay, so if that's an expression for the order size and that's an expression for the lot size, let me see. D dollars to store 1 unit for a year. How many times per year should the store reorder? Order size and lot size. When Q is this, okay, we'll put that in later. We just got to get the main structure. A store sells this many units. It costs some amount to store it. So we have the storage costs plus the ordering costs. Okay. So then we got to think about how much does it cost to store it? It costs D dollars to store 1 unit for a year. And then how much does it cost to reorder it? So in order to reorder it, it's going to be B plus C times the number of units. Okay. Let me go to view an example right here. Let me zoom out some. Okay, right there. So it says to find out how many times per year the store should reorder, substitute the values into and simplify. 4 parts. That's fine. That's not a big deal. To find the lot size, substitute this, okay. Therefore, the store should order 20 units per year to minute. Oh, they gave us all the parts. We just plug it in and that's it. Oh, I think we were overthinking this. How many times per year substitute those values into this and simplify? So the order size, okay. So this one is a lot more simple than what they gave us, what we worked on the other day, where because they gave us the formulas, right? We didn't have to try to find those. What it costs to order was given, so we just plug in the components and simplify, and then the lot size, substitute the values of into and simplify, right? Therefore, it should be 20 units 5 times per year. Okay. So yeah, we just plug in what was given, right? So let me see. Order. The store should order that many, and okay. So I guess I'll just write it here. I need to get my calculator back. So yeah, we got kind of lucky with this one. I think we're just gonna plug in what was given. It's not like we were doing it from scratch. Like in the other one, I know we were doing it from scratch. Let's get rid of this, okay? Okay, so what I'm gonna do, in my calculator, we have a function called store. So for instance, I'm gonna put 105, and I wanna store this as, I'm gonna hit alpha Q, which is MNOP. Q is right there. I'm gonna hit alpha Q. Okay, so I went on to store that for Q. I want to store 10 stored as alpha D. I think this should work. Okay. 21 stored as alpha B. Okay. And 18 stored as alpha C. Okay. So now I think I can just go square root. Now the numerator is QD, so I'm just going to put alpha Q, alpha D. Okay. Close parentheses, I'm going to say divided by, the bottom is 2 times alpha B. Okay, and we need to close out the square root. And we get 5. So I'm going to put a 5 here. Well, I'll put 5 there in just a moment. And then for the lot size, I'm just going to say the square root. I'm basically just plugging all this stuff in. The numerator is 2 alpha B, alpha Q, divided by the denominator is just D, alpha D. Okay, close out the square root. So she'll order 5 units 21 times per year. Hmm. 21 units 5 times per year. Maybe we got it backwards. Let me just try that real quick. Oh, it cut off. Okay. If that doesn't work, then we'll get to the bottom of it. Lot size, order size. That's kind of weird, but anywho. All right, so the viewing example was like they went on and just gave us those parts. We didn't have to do it from scratch like the last one. So then we were good to go there. Okay. Okay, this is dead. Oh, let's plug this in. Oh, did you want to ask any questions on these, or I know you probably have more, but I think I'm burnt out. Did you want to ask any other questions about what we went over today?
No, sir.
Okay. All right, so we'll try again on what's today, Monday. So we'll do some more on Wednesday. Okay.
Okay.
You ever try working on some of these with the tutors?
Yeah.
How are they?
Okay.
They're good. Okay.
Yeah.
Okay. All right. Well, I'll see you on Wednesday.
Okay. Bye.
Peace. All right. Oh.